Hello and welcome to this webinar hosted by the Institution of Mechanical Engineers and presented by SimScale. My name is Robin Salfas, I'm Programme Development Lead at the institution, and I'm delighted to introduce today's speaker, David Short. David is the Product Manager for Structural Mechanics at SimScale and brings with him years of professional experience in computer-aided engineering with a background in marine. He's committed to helping organisations discover the benefits of early-stage simulation and works to make non-linear and dynamic FEA applications accessible to design engineers worldwide. Without further ado, I'll hand over to David. David, thanks for joining us today.
Perfect. Thanks so much, Robin, and welcome everybody. Yes, so as Robin mentioned, I'm the product manager of SimScale. Now, I'm hoping a number of you already know SimScale, and for those of you that do, you'll be getting to know a few particular applications that we're really focusing on at the moment in the electric vehicle industry. And for those of you who are new to SimScale, I'll also introduce SimScale, the main concept, and then we'll see the focus of today's webinar. So today's webinar, we are going to be looking at predicting structural risk in EV components. Okay. In terms of an agenda, we will first look at advanced structural analysis with SimScale. So that's really what we're focusing on here, and then we'll get into some specific industry relevant applications, and we'll do a deep dive into battery vibration and shock analysis using cloud native parallel computational finite element analysis. Now, if you do have any questions at any point, please do type them into the question chat, and then Robin will ask me the questions at the end. So really, do please reach out if you have any questions or comments to discuss. So SimScale. SimScale is all about making advanced structural analysis truly accessible. Now, the way we do that is we provide a 100% cloud native simulation platform. Now, that means it's web browser based, and it means that everything you're doing in terms of the simulation computation is running in remote servers. That means we are not connected to your local hardware in any way, and it means you can scale your simulations both in terms of the number of simulations you want to run in parallel, and the size of the models that you want to run as well. So for a smaller mesh, we'll be running on a smaller machine, and for a larger mesh and a more complex case, for example, a dynamic simulation, we'll be running on a much larger instance with more storage and higher compute power. So it really is just one platform where we have all of our physics in one streamlined and intuitive workflow. So you'll have fluid analysis, you'll have thermal analysis, structural analysis, all in the same environment. So you can really chop and change. Once you've learned one simulation type in SimScale, then you might be able to jump into fluid analysis, for example. Take an electric motor, for example. You might want to do the pressure drop and the thermal distribution of the cooling channels using CFD analysis. And then you might want to extend that into a thermomechanical structural simulation using what I'm responsible for, the advanced structural analysis tools that we have on offer. Now, we have one license type, and that includes all the nonlinear and dynamic features. So we really aim to get you started in simulation, but also extend your knowledge and extend your capabilities into the more advanced simulation types that really benefit from cloud simulations. So for nonlinear and dynamic analysis, where you have to solve multiple quasi-static time steps or physical time steps, it really makes a big difference to be able to run these simulations in parallel, because they do take a lot of compute resources. And traditionally on local hardware, that would be taking up your entire workstation, and you wouldn't be able to get on with any other jobs on your computer. That is not the case with SimScale. Everything's running in parallel in the cloud, and you can keep working as your simulations are running. One thing I really want to mention is the fact that we offer support, real-time support in the platform itself. So whenever you have a question, then you can jump onto the in-platform chat, and that's where our support engineers are there, and they're really dedicated to making sure they're solving the problem when you experience it, not a week later after submitting a ticket or something like this. It's very live, and that's really enabled by the fact that we are completely cloud-based, right? So if you want, you can share the project with us, and we can directly jump into it and offer support then and there. So for those of you who are new to simulation and are looking to sort of dip your toe in the water, so what does simulation really bring? It brings a number of things. So that's both in terms of the design exploration, so low-cost design space exploration. With simulation, you can go really fast through design iterations and make sure you're focusing on the high potential candidates up front. We can disregard the low potential ones that might fail in physical testing before we even get to the prototyping step. Now, exploration also means innovation. So when you're running simulations, it can also show you things that you weren't expecting, right? You can really start to understand exactly how the structural mechanics behave, how the kinematics of your parts interact with one another, and that kind of detail you just don't get from physical testing. That's really one of the main benefits, is the fact that when we compare against physical testing, you get point-wise data for the whole structure. So you can really detail where's the structural risk and how can I mitigate those risks as well. And we'll go through an exact application around batteries, and we'll have a look at how that looks like in practice. Now, in terms of the applications that we offer in the advanced structural analysis field, specifically for EV components, we have a lot of customers doing battery module vibration and shock. We also have many customers doing electric motor, rotor and shaft interference fitting. Right, so it may not look like the most complicated simulation, but it really is, because you need to solve this initial penetration, which then you'll see the stresses in your rotor cage. You can run that at multiple temperatures to really understand the interference fitting sizing. You can run it with nonlinear material properties to understand how much plastic or permanent deformation you have in your rotor cage. So you can do a lot of work up front to know exactly what is the interference fit I need to, number one, establish reasonable contact pressure, and number two, where that's going to break, like what's the actual limit. So you can do a full sizing before you actually get to prototyping. Also, on the subject of electric motors, we also offer rotor dynamics. So on modal simulations, we can include the gyroscopic effects, which allows you to understand the rotational eigenfrequencies, and also the effect that the rotational speed will have on those eigenfrequencies. Right, so that would allow you to create a Campbell diagram and understand the critical speeds for your application. So let's get into a real case study, right? So today we'll look at a battery module assessment. We've taken a electric cargo vehicle here, and we've got the battery unit that we want to simulate and assess. So it's a 22-cell EV battery with a gross mass of 46 kilograms. Now that places it as a large battery classed under UN and AIS standards. And let's think firstly physically what we need to do with this kind of product. So we know that when you've designed the product, it's going to have to go through physical testing. Number one, it's going to have to go through vibration testing on a shaker table, like what's in here. And that shake profile, so the level, the amplitude of the oscillations is set by the international standards. So that could be MIL standard, that could be UN standards, and many others, ISO for another few. And then once we've actually had a look at so it needs to be able to survive that vibration testing, right? And we can also replicate that exactly on a simulation, on a simulation front. So what we will do is we will have a look at checking for resonance within the frequencies that it needs to be physically tested at. And then if we find a natural frequency within that testing range, right, we know that's critical. We should, number one, avoid that entirely. But if there is a natural frequency within that range, then we need to really dive into the details of it. What is the damage? What is the actual chance of failure in that physical test? And we can do that on the simulation front, which allows us to then disregard a poor candidate before we even get to physical testing. Now, these physical tests are very expensive, and it makes a lot of sense to be doing these simulations up front, right? So we can sort of make sure that we're really focusing on the good design candidates. Now, secondly, what we need to make sure is it needs to be able to survive shock testing as well. So here's another little video of what a shock test looks like in reality. So that's a single direction shock test, and we'll do exactly the same in the simulation environment. Just like in the vibration testing, we can then understand the peak stresses, the maximum accelerations, and really understand which components are likely to fail, or if it's all good and we're ready to go through to prototyping. So I'll take you through that process, and then we'll have a look at the SimScale platform as well, so that you can see it in reality. So what we first do when we're thinking about vibration testing is first run a modal analysis to understand what are the natural frequencies of our battery module. So I've run a modal analysis that I'll show you in a minute to capture the first 10 modes, so the lowest energy modes, the ones that are most likely to be excited. And we can see that we've actually captured the first mode coming in at about 146 hertz. Now, if we go back a slide, we can see that we need to make sure that we need to check for resonance between 0 and 200 hertz, according to these standards. And we can see we've got a dangerous mode. We've got a critical mode that we need to understand the structural risk around that mode. We can see what that mode looks like. So it's basically a translational mode, all in the X direction, essentially. And it's basically oscillating about the clamps that we're holding the battery with. Okay, so we need to make sure that if we go through with this product, we want to understand how likely is failure at this critical eigenfrequency. Okay, so what we can do then is move on from a modal analysis into a harmonic analysis, where we can run the same scenario but give it a physical shake, just like in the physical test space. So what we will do is we will input an excitation of 2G, and that'll be a sinusoidal base excitation in the X direction. So really trying to replicate or trying to excite this mode of interest. So we'll shake it in the X direction. And what we'll do is we'll drive the excitation at frequencies between 140 and 150 hertz, right? So we want to capture the peak accelerations, the peak stresses of the first mode. So I'm really only focusing on the first mode here. You can also extend a harmonic analysis to look at all the modes, but as we've only got one critical mode of interest, we're just going to look for the mode at 146 hertz, and we'll run 10 frequencies around it so that we really capture the peak. Now, I've added 5% damping to the material in the model. So when we go into a dynamic response analysis like this harmonic one, we need to make sure that we've also got the damping, the physical damping in the model as well, so that we don't see infinite resonance, right? If you don't add damping and you drive it at a critical frequency, then you will have infinite response, right? Which is definitely not physical. And what you can do in SimScale is you can very easily test out at 5% damping, or test out at 2%, 1%. Look at a worst case scenario of 1%, for example. And if your product survives that at 1%, then you're all good. But here I'm just using a fairly moderate damping value of 5%. Okay, and that's 5% of the critical damping ratio. So first look at the results. Our input acceleration was at 2G, and our peak acceleration output was actually already at 28 G. So a large dynamic amplification factor we can see here. We see a peak displacement of 0.4 millimeters. Now, when we look at the relative displacements between the parts, that's really what can be critical to understand if we have clearance issues within our battery module. So say, for example, you've got a plate next to a casing, and there's only 0.1 millimeters spacing between it. I mean, that's a little bit small. But then we would be very concerned about a peak displacement of 0.4 millimeters, because that's going to have effects on noise. It's going to have effect on the structural integrity as well. Maybe bolt unfastening and things like this due to the knocking between the parts, right? So you can, number one, see your peak accelerations, but you can also see the displacements and check if that is going to affect clearance issues within your model. Now we see the most critical excitation actually happening at 147 hertz, as we did the 10 frequencies around the 146 hertz in the modal analysis, and we find that the peak is at 147. This is likely due to the slight difference when we add damping, that mode might have shifted just a touch. So that's really why it's important to look at a spread over modes, not just drive at the modal at the eigenfrequency from the modal analysis. Now, if we dig in a little bit deeper, we can see which components are at risk by actually assessing the capacity of those materials and seeing how much yielding we actually have in those components made of different materials. So here I've got the 3 components I've identified as at risk: copper bus bars, the PVC holders, and the steel casing. Now, each of those have the yield strengths as we see here. And what I've done is a quick plot of each of those components with the yielding shown in white. So anywhere in white, we actually have stresses going above the yield strength of the material. And that's obviously something we want to avoid, right? That's going to lead to permanent deformation. In some cases, it might be acceptable, but generally, we're looking at safety factors of a minimum of 2, really, so half of the yield strength, right? So this is already pretty dangerous territory that we see for all of these components. That we have some pretty large areas of yielding for the PVC holders. The copper bus bars are getting close to yield, but they're not completely at yield. So the peak stresses were at 21 megapascals, and the yield is at 30 megapascals, and that's a minimum safety factor of 1.4. So still, that's dangerous territory, and we would likely, it depends from company to company, from standard to standard, we like to be designing at minimum safety factors much higher than that. Okay. So the outcomes of this kind of simulation of the vibration testing is that there's moderate risk of failure for the PVC holders and the casing and the bus bars, specifically during the vibration testing. But one thing that we also have to consider is the risk of fatigue damage as well. Now, fatigue will happen at stresses much lower than the yield strength, right? And because these products are going to be exposed to a lot of vibration, a lot of repetitive loading, we really need to make sure we're considering fatigue damage as well during the product lifetime. So although it might survive the vibration testing, likely fatigue failure would be caused when we stick to this design. Okay, let's have a look at the shock analysis. So for the shock analysis, we'll use a dynamic analysis, and we'll run a 50G 11 millisecond half sine shock in the X direction. Again, I'm using a moderate value of damping of 5%. And what we want to make sure is that we're replicating this half sine shock profile that is stipulated by many international standards, right? So that could be the DO-160G for aerospace and airborne electronics components, or for MIL standard in the US, and also for the UN 38.3 T4 testing standard as well, right? So we're replicating this exact profile, and we're hitting the same battery module with this profile. And there we can see here, I've used the same scale. If I just go back a second, we don't see a huge amount of stress of peak stress areas outside of these sort of on the PVC holders. But when we go to the shock analysis, there we see a considerable amount of stress being carried in both the support structures throughout the PVC holders, and a lot in the case as well. So digging into the results, just like we did for the vibration analysis, we see significant yielding for all three of the components that we consider to be at risk, even for the vibration test. So looking at the steel casing, we see significantly more yielding than we saw in the vibration analysis in the case. The same goes for the PVC holder, where you see significantly it is drawn into the center of the holders as well. And again, for the copper bus bars as well, there we see stresses going above yield strength on these components. So as an outcome here, we see significant risk of failure of all three of these components, and we haven't even looked at the support bars as well. But at this point, it's pretty safe to say that this design candidate is not going to pass our shock testing, not without experiencing a significant amount of permanent damage. So let me show you what that looks like in the platform itself. So I will bring SimScale into the picture now. So I'm hoping you can all see my screen here. And you'll see that SimScale is purely web-based, right? So I'm accessing the software directly through my browser, okay? And that means it's accessible from anywhere. It's accessible at any time. And because the simulations themselves run not on your local machines, they run on remote servers or cloud instances, your simulations can scale as well, dependent on the model size. So here we've got a mesh size of 1.2 million nodes. So we're going to be running this on a fairly large machine, right, to capture to make sure we have an efficient solution here. Okay. But I won't get straight into meshing. No one wants to go straight into meshing. We'll talk about that in a little bit. So back to the SimScale platform itself, it can be accessed from anywhere, at any time, and at any scale. What you need to do is you bring in your geometry from a CAD tool, be it Onshape, be it Inventor, be it SolidWorks, wherever. So we'll read any CAD files that you give us. You bring it into SimScale. You can edit the CAD to get it ready for simulation, for example, deleting surfaces, creating fluid volumes for CFD, for example. So we've got our own CAD tools as well. And then you go to starting your simulation. You'll notice that I've got 3 simulations here. So the modal survey, the vibration testing, and the shock testing as well. And that's what's quite nice is you've got your full project in one place with multiple simulations, with multiple runs underneath them as well. And all of that can be running at the same time as well. So what I've done is I've gone in and created from our simulation library a modal analysis, I've got a frequency analysis, and then a harmonic analysis, and also a dynamic analysis. If we look quickly at the setup for a modal analysis, you can see that we can see that in action. Right? Let me just create a new one. The first thing it will do is it will automatically detect the contacts within the model, and then you can go through and you can check out all of your contacts. You add your materials either from our default library through your own user materials, your custom materials, or through a company library as well. And then you'll be setting up your boundary conditions, which is then the physics of the problem. There's a lot of automation going on, but you can manually refine, you can manually customize any of the settings that we give, that we offer here. So you'll see that by default, we're taking care of the numerics and the simulation control, the element technology, but you can always go in there and adapt those to your applications or to your previous experience, for example. So let me delete that. I've run the modal analysis with these materials, just basic linear materials for a modal analysis. It's the linear simulation. And then I've added some boundary conditions. I've added the fixations where the product is clamped during the vibration and shock testing. And I've also added some constraint on the base as well, where it's connected to the table. I've used automatic meshing in this case. So just a fineness of 5 for giving us our 1.2 million cell mesh. Now we offer both tetrahedral element meshing as well as hexahedral and prismatic elements, first and second order. Then we can run our simulation. I've run one for specifically just within the the range in the UN 38.3 T3 test phase, but I've also run one from 0 to 1000 hertz just to really capture or to understand what's happening with all of the modes of interest. So from here you can see your eigenfrequency plot going up to, we've got the 43rd mode up at nearly 1000 hertz, and our first mode, our critical dangerous mode, is the 146, which we've already had a quick look at. And you can animate these simulation results, and you can go in and adapt, customize your result outputs as well. Now let's do something a little bit more interesting and set off some simulations. So we've got our harmonic vibration analysis. We've already gone through the sort of design outcomes of this analysis. The setup is exactly the same as the modal analysis, except we add a physical base excitation in the X direction here Now I can also change this and say I want to actually have my base excitation in the Y direction. Now we'll go with the Z direction because we don't want to shake it into the. Any of them will be fine. We can do both. So let's now say this is base excitation. Just call it 2G for now, and we'll do it in the Z direction. So then I can go and I can start a simulation here. So we go 2G in Z, and we set off that simulation. So that will jump off into the cloud, and the simulation will get started. And what we can also do is we can set up another simulation. Hit it with another 2G in Y. Okay, and we'll see that these simulations then are sent into the cloud. Well, everything's in the cloud, right? We're setting up the problem in the cloud as well. But these simulations will then run in parallel. Now that's a huge advantage when it comes to these slightly longer simulations, particularly with the shock analysis as well, where we want to have, well, we know within our international standards, we have to do 3-directional shock testing. We need to do a half-sine pulse in the X direction, the Y direction, and the Z direction. With SimScale, we can run all of those at the same time, whereas with a local machine, you might need to wait for one to finish before you start the next one, and so on and so forth. So that's a huge advantage to using a cloud-native solution. Okay, so there was a few insights of how SimScale looks like. Hopefully, you've got a bit of a feel for what we're all about. Do we need to look at the dynamic analysis? No, I want to wrap it up a little bit so that we've finished it in half an hour, and then there's going to be some time for questions. Yeah, you've now got an impression of what SimScale is all about. And let me jump back to the slides. Okay, so in summary, with our deep dive, our investigation of this EV battery unit, we can see that the simulations have highlighted significant risk for the steel casing, for the PVC holders, and the copper bus bars, both in vibration testing and also in the mechanical shock testing. So what's great now is we can disqualify this design before even going to prototyping. So we're not going to waste any money on a physical test that we know the product will fail, right? And what's always surprising for our customers is that one physical test of an EV battery costs more than a SimScale license. Right, so you can have huge cost savings by just doing simulation up front, making sure that you're disqualifying poor designs, and actually you've got the detail as well to mitigate those poor designs and understand what's going wrong, how we can change it, and what we can do as a next iteration. So it's really simulation-driven design. Okay. And with the complete detail of the stress and deformation, we can pinpoint those areas of risk. That's what I'm basically just saying, and check for the clearance issues. So remember, we can easily show which components are deforming the most, and whether or not that's going to cause noise issues, which is obviously a huge problem in the EV world. Everyone wants a very quiet EV. And so the more detail you can have there, the more satisfied your customer is going to be. So I've highlighted a few potential next steps for the battery modules design. We can we can reconsider the steel casing fixation, because we saw a lot of stress building up around those fixation areas. Now, some of that will be stress concentration or stress singularities due to the boundary condition, but there was quite a region of peak stress around those fixations as well. So we could think of a different clamping strategy, for example. That could be one simple step to improve this design. We can optimize material selection, so maybe use a slightly stiffer material or a softer material, and see how that will affect the peak stresses in the PVC holders, for example, in the copper bus bars. And we can also consider adding maybe some more innovative things like gap filler material, right? The sort of foam that you can press into tight spaces to damp out vibration, or with different types of rubbers that you can use to actually damp out any vibration and reduce those peak stresses as well. Okay. So I hope that was interesting. I've had you here for 30 minutes or so. Now, if you have any specific questions for me that I don't answer today, please don't hesitate to reach out to me personally. I love hearing from both prospective customers and our current customers. If you want to go down straight down the sales route, then you can request a demo by contacting the sales team, and then we'll have the application engineers get in touch with you. But yeah, so what I would do now is I would ask Robin if we've actually had any questions coming in over the chat.
Yeah, thanks a lot for that presentation, David. That was really fantastic and very well delivered. Thanks a lot. Yeah, we've actually already had a couple of questions coming in, so if you're happy to take those, I'll start putting those to you. The first question is coming in from Simon Hart from Arrow, who's asking if you could expand on how you decide appropriate levels of damping. So, for example, 5% of critical damping.
Yeah, sure. So to be honest, I've guessed at this one. So for a general assembly made out of steels and different metals, it's very, very hard to get an accurate damping value. So best practice is really to do a number of simulations, one at 1%, sort of global damping, one at 2%, one at 5%, for example, and then deliver report all of those stress values, right? It's very, very hard to get an accurate damping value for your entire assembly. Yes, you can get damping values for the specific materials, but once you connect them, you need to consider the damping of the contacts themselves as well. So it's very unlikely you can get a very accurate value for damping, and best practice is actually to, as I say, run a number of simulations at different damping values. And with SimScale, you can run all of those simulations in parallel, right? You know, the setup's exactly the same, but you want to do it at 3 different damping levels, then you can run all those simulations at the same time. So that's a big time saver there. So I hope I've answered your question there, but please, if I haven't, give me an email as well. If you want to learn more about the damping methods we use, Rayleigh damping, modal damping, and whatnot. I mean, we've only got 45 minutes here today, so I don't want to go into super technical details, but please do reach out if you're interested.
Yeah, we've got another one here from David Hughes from WAE, who's asking, well, first of all, he's complimenting the presentation on seeming to sounds very efficient process-wise, but he's wondering if it would be appropriate for bus bar analysis, and he's also asking if it can analyze bolts in connections, or you can output bolt forces at the interfaces.
Yeah, absolutely. Thanks for the question. So bus bar analysis, I take it you're actually thinking about the electromagnetics of the bus bars themselves. So we've just recently brought on an electromagnetics module, right? So definitely get online and check that out. I don't know a lot of detail about bus bar analysis specifically, but obviously from my part, you know, we would be interested in the electromagnetic power values, and then bringing that into a thermal analysis and bring that into a thermal mechanical analysis to check the mechanical stresses due to the electromagnetic conductance in the bus bars themselves. But as I said, I don't know much about bus bars at all. But I would imagine this is an application for our electromagnetics product, which is again in the same platform with the same workflows. So it's very easy to jump from FEA into the field like that as well. In terms of bolts in connections, yes, absolutely. So what we do is we model 3D bolts. So you'll need to model your bolts in 3D, and then you can add bolt preload boundary conditions and calculate reaction forces on the bolt heads, for example, to then go into your bolt hand calculation tool. I can't remember what they're called, but where you do the actual bolt sizing using your reaction forces from SimScale FEA. That's the current workflow. What we're also working on are specific connector elements themselves. So we're bringing out pin connectors, or we've just brought out pin connectors, if you want to give it a spin, where we will define, for example, without modeling the pin, you'll define your cylindrical surfaces which are connected by a pin. We'll define a kinematic relation between those surfaces, and we're going to do the same for bolts as well, that you can then add the preload, and you can then extract the shear and the tensile forces on those connectors themselves. So bolt connectors themselves are work in progress, but our current workflow is going down the 3D route to then extract reaction forces and take it into your bolt hand calcs.
Good stuff. There's another question here from Ian Mearns. This is just two-parter, so I'll probably address these one at a time. So number one was, how can these simulations be applied to wiring fatigue, for example?
Wow, that's I think that's a little bit over my head, to be honest. Wiring fatigue, I don't know much about it, right? But what our customers do in terms of fatigue is they'll be calculating peak stresses, and then they'll be using manual workflows in line with, for example, the FKM guideline or the ASME guidelines in the US for actually creating the SN curves, and then taking the stress results from SimScale and assessing the product life cycle there as well. What we are developing at the moment as well is a download option for use in a fatigue tool called Encode. Now, I don't know. As I said, I don't know much about wiring fatigue, so maybe it's worth giving me an email with a few more details, and I can look into the question in a little bit more thoroughly. Now, there was a second question. Sorry, Robin, did you ask me? Okay.
Yeah. Part two of that was actually, I'm glad someone's asked this, because I was wondering this myself. It was about simulations validation. Do you conduct physical tests to sort of validate the outcomes of your design simulations before producing? Or
yes, absolutely. So obviously, our customers are validating SimScale on a daily basis. When they're running their simulations, they're also corroborating that with the physical testing that they're doing. So we've got a lot of case studies where we see comparisons between physical test data and the simulation data. In terms of the solvers themselves, the actual simulation processes, we have a big library of validation cases, right, that shows for this element type in this scenario, how close do we get to the analytical solution, just like you'll see in all of the large simulation software providers. So we've got a big wealth of validation projects on simscale.com. So just type in simscale.com validation cases, and you'll see hundreds, 50 or so really structural analysis specific validation cases. So really do have a look through those, and it ranges from linear static into thermal into dynamic and so on.
Okay, and there's one more here, which is asking about how you linearize contacts for modal analysis.
Good question, very good question. So this is on our roadmap, right? So it's on my radar that we need to consider a better linearization approach. So at the moment, we only have the option for linearizing manually, right? So we'll set up your simulation. You've got either bonded contacts or sliding contacts for your linear modal analysis. We haven't yet gone down the route of first run a non-linear analysis with a bolt preload, for example, and then measure where you have surface-to-surface contact and then apply that only as bonded contact, right? So we haven't gone down that route at the moment. It's a manual approach. You'll have to say either this whole surface is bonded or this whole surface is sliding, or you really take a look at your non-linear analysis. You see where the surfaces are touching, and you'll have to then split those surfaces in CAD and bond them together. So a very manual process. So I've heard this a lot from a few customers, but it's on the quite advanced stages. So not many of our customers really want this right in the design phase, but more on the validation side further down further into the development process. Right, yeah, I would love to also talk to you about that. These are fantastic questions. So please do get in touch so we can discuss them in a little bit more detail.
Well, no, clearly you've inspired our audience, so thanks a lot, David. I think that's it for the questions that I can see at the moment. So unless there was anything else you wanted to say, it's all it remains for me to do is to thank you and your colleagues at SimScale so much for sort of for delivering this today. It's really really appreciated, and thanks to everyone in our audience for joining us today for this webinar.
Fantastic, and well, thank you very much, Meki, for having us. So that was fantastic. I hope you all learned something, and yeah, it'd be great to stick in touch. So thanks a lot.
Terrific.